Hello. Yep. How is everybody? Uh, so something I realized yesterday while doing a few dry runs was that I was going a couple minutes above the time limit. So if I'm going a little fast, you can come up to me later, ask questions, or just complain, and I will apologize. So a little bit about myself. I'm Raghav Roy, and I'm an engineer at VMware, and I work with network virtualization with the ESXi hypervisor stuff. And when I'm working with Go, is generally when I'm contributing open source, sometimes to Kubernetes, or just on my personal projects. So to set the expectations of the talk a little bit, I'll be talking about subroutines and how coroutines can be explained in terms of generalized subroutines, how it all started, what the history of coroutines is, and why they were brought up in the first place. We'll try to classify coroutines, and we'll try to build up to what a full coroutine means and why we are interested in that. Of course, we cover coroutines in Go, how we can implement coroutines in Go using existing definitions, and also some Go runtime changes to support them natively. So yeah, let's start up with some basics. What are subroutines? So subroutines or function calls can do a few things. They can suspend themselves and they can run another subroutine, or they can terminate themselves and yield back control to the caller. So this is what it would look like. Say you have three subroutines over here. The first one suspends itself, starts running. This is just so that you get used to the notations that I've used a little bit. So the first one suspends itself, starts another subroutine, which can then suspend itself, start another subroutine. And the only way that this can yield back control to its caller is by terminating. So it terminates, yields back control to the caller, which then can terminate and yield back control to its caller. So this is how a regular function call would work, right? So yeah, another thing is the eager and closed, depending on where you're looking, these definitions change, but for the context of this talk, when I say eager, I mean expressions that are encountered by a subroutine are evaluated as soon as they're encountered, and closed means that it only returns after it has evaluated the expression. So it can't sort of suspend itself in the middle of an expression. So let's try to define coroutines with what we know so far. What coroutine can do is, when I say generalized, it means that it can do everything a subroutine can, which means that it can suspend itself, run another subroutine or coroutine, terminate itself and yield back control. The magic thing that a coroutine can do is suspend itself in the middle of an execution and yield back control to its caller. So how would that look like? Say we have a subroutine running, and the subroutine wants to start another coroutine. So it starts it now, or resumes it. Now, when the coroutine needs to suspend its execution, it can suspend itself in the middle of the execution, yield back control with some output that the subroutine may be interested in, and the subroutine can then resume the coroutine again. The coroutine can yield back control to the subroutine, and so on and so forth, sort of like a direct message passing that's happening between these two processes. So this is how it would look like. At the end, you reach the end of the file, for example, and both of them can terminate. So essentially, coroutines are like functions that can return multiple times and keep their state, which could include the local variables, the command pointer, things like that. And so they can resume from where they yielded. They can resume from where they last suspended. So let's look at an example. And let's try comparing binary trees. So in a classical way, you would design some sort of a recursive algorithm where you go to the end of the stack and you start returning values till you have compared compared all the nodes. So just so that you can wrap your head around a little bit with how you would implement this in a coroutine fashion, is you have your function visit, which is visiting all the nodes of the tree in sort of like an in-order fashion. And instead of returning, you are actually yielding back control with the output to your caller function, which in this case is that CMP function. And this is, I think, the CLU example that Russ uses in his proposal. So yeah, over here we initialize two coroutines, and these resume functions work concurrently. And that's another thing that I keep talking about again and again, which is important to coroutines. So you resume your visit function with the head of the tree, head of the first tree, for example, and it visits all the left nodes till it reaches the last left node, and then it yields back the value 2, where it sort of the leftmost node in this case. And then what happens is your second coroutine starts running, and it does the same thing. It makes a call to your visit function, which yields, and then you have your value 2 over here as well. It yields back control with the value 2. And then you can go ahead and compare these nodes, and so on and so forth. You go to the right node. This way you have sort of like a context switch that's happening between two coroutines that are calling this visit function again and again. And this is happening concurrently and not parallelly. So that's something that you can keep in mind. So yeah, let's go back in time. It's 1958, and you want to compile your COBOL program in the modern 9-path COBOL compiler. That's Grace Hopper, by the way. It was her birthday recently, so it made sense to add her picture there. And also, she's one of the co-developers of COBOL. So you want to take a main program which actually has physical punched cards, and you want to pass it to your basic symbol reducer, which will eat these punched cards and spew out the tokens onto the tape. By the way, if you don't understand what a basic symbol reducer is or a name reducer is, that's fine. Basically, these are processes that are interested in the output that is output by the other process. So a name reducer is interested in the outputs of the basic symbol reducer, and vice versa. So what happens then is that your basic symbol reducer returns all these values or writes onto the tape and yields back control to your main program. Your main program calls your name reducer or your name lookup, like what it's called today, which outputs its own tapes, and then this is the control is yield back to your main program, which calls the basic symbol reducer, and so on and so forth. So like our subroutine diagram, it's essentially what it will look like. You have your main function calling a symbol reducer, it writes onto the tape, yields back control, and so on. So at the end of this, what you're left with is a bunch of extra tapes that you don't need anymore. And you make use of this very heavy machinery behind the scenes with these punch cards and creating all these tokens and things like that. And Conway actually thought that there had to be a better way to pass a token from a lexer to a parser without all this expensive machinery. And what he realized was what we've already discussed, that subroutines were just a special case of more generalized coroutines, and that you didn't need to write on the tape, which means that you didn't need to return, and you could have this message exchange happening more directly, bypassing this entire machinery. So like our coroutine diagram, this is what it starts looking like. Your symbol reducer, every time your name lookup wants to read a token, it can just call into this symbol reducer that is actually running as a coroutine, which can suspend itself once it has a token, yield control back to your name lookup. Whenever it wants to read the next token, it calls into the subroutine, and they go on back and forth till you have all the tokens that you want. So this way, we're actually raising the level of abstraction, and it led to a less costly control structure, leading to the 1-pass COBOL compiler from the 9-pass COBOL compiler. And this is an example of negative cost abstraction, which means increasing the abstraction while reducing the cost of your process. Side note, this was the paper that actually coined the term coroutines, and I've linked to this. It's a super interesting read. It's about the COBOL 1-pass compiler, the design of separable transition diagram compiler. It's a mouthful, but yeah, great paper. So where are coroutines now? Considering all that we've talked about, coroutines should have been a common pattern that is provided by most languages. But with a few rare exceptions like Simula, few languages actually do provide this. And you may be thinking that you know a few languages that do, but actually probably the ones that you're thinking of provide like limited variants of these coroutines, and we discuss this a little later. So the few problems with this is that generally there's a lack of uniform view of this concept, and there are no really precise definitions on it that everybody agrees on. And Another interesting thing, why it's not provided in mainstream languages was actually the advent of Algol 60. And with that, you didn't need to have your parameters and your variables stored as global variables. Instead, you could have block scope variables, which means that you could have it stored relative to a stack pointer. And how does it look like now? This is, I mean, I'm sure everybody's used to seeing something like this. You have your stack where you have the activation record of your function, which means it has all the locals, it has the return addresses, the parameters, and your stack pointer sort of points to the topmost frame. And as it calls more and more subroutines, the stack sort of grows upwards and the stack pointer moves with it. Now, how would you want to implement a coroutine in this sort of a paradigm? Well, one way could be you have your subroutine running over here, and if you want to start a coroutine, it would have to sort of be in like a side stack. And your coroutine could have its activation records along with the saved registers, which you need because you are, whenever the coroutine suspends and resumes again, you need to start running it from where it's suspended. So your stack pointer now has to move and point to the top of the frame there. This coroutine can then go ahead and call even more coroutines, and the stack sort of grows that way as well. What happens if you have another subroutine that is interested in this coroutine? Well, you would have to have another stack where that subroutine is running, and you have to move your save registers and your stack pointer around. So do you see what's happening here? We are mimicking sort of heavy multi-threading, which is increasing your memory footprint, instead of the cheap abstraction that a coroutine was meant to be. And well, that becomes a problem. And another problem that we talked about was no precise definitions for it. The most widely accepted sort of thing is Marlin's doctoral theses. And these are all things that we've already talked about. And basically, formally, it formalizes that the data local to a coroutine persists between successive calls that we've seen even with the binary comparison example. And the execution of a coroutine is suspended as control leaves it, and it carries on from where it left off as the control re-enters the coroutine at some later stage, right? So now that we have the basics and the history out of the way, and hopefully made a case for its usefulness, let's build up to what a coroutine can look like in Go. But before that, we need to classify the coroutines a little bit to see what a full coroutine is, and we get to the Go goodness pretty quick. So yeah, bear with me. So by doing this, we see what we mean by a full coroutine and why we're interested in that, and how some languages like Python and Kotlin have implementations of coroutines, but they don't actually provide this. So another thing, these few next slides, I haven't added the code snippets for it, so you sort of have to take me on my word, but I have added links to it, which you should definitely check out. So the first classification is the control transfer mechanism between coroutines. So they can be defined in two ways. One is symmetric, which means that there is only one sort of control transfer operation that happens where your coroutines explicitly pass control amongst themselves. But we are interested in asymmetric coroutines, where you have two control transfer operations, something that we already talked about, which means there is one control which invokes the coroutine or resumes the coroutine, and one that suspends it or yields the coroutine, and you can yield back to its caller. And the latter, returns the control to the invoker. So coroutine mechanisms that are used for concurrent programming usually provide symmetric coroutines, and when you have something like generating sequences of values like generators or iterators, you have asymmetric coroutines. But the good news is that we can actually emulate or implement symmetric coroutines using asymmetric coroutines, and they are way easy to write and maintain. In fact, like the paper that I've linked to, which has these, I couldn't even wrap my head around how the symmetric coroutine is implemented. So if someone understands it, please come up to me and explain it. But yeah, another classification is first class and constrained coroutines. So having coroutines, like we saw again in the binary comparison example, given as first class objects that are fully programmable by the user has a huge influence on the expressive power. But if your coroutine is constrained within the language and the programmer doesn't have a lot of influence on it, it sort of becomes, it sort of limits of what you can do with the coroutine. And when I mean first class, I mean your coroutine can appear in an expression, it can be assigned to a variable, can be used as an argument, or can be returned by a function call. So these are things that sort of improve how you can work with the coroutine. Finally, an important one is stackfulness, which means that your coroutines are allowed to suspend their execution from within sort of nested stacks or like nested functions. The coroutine and your invoker need not be on the topmost frame to yield back control between themselves. They can be wherever in the function stack, and they can sort of yield back control. And this lets us do some more general purpose multitasking and multiprocessing stuff. Yeah, so why Python and Kotlin, like I mentioned, aren't full coroutines is because they aren't stackless. So so it sort of limits what you can do with them. So yeah, we show that for a coroutine to be a full coroutine, it would have to be stackful and be provided as first class objects. And full coroutines can do everything that a Python or a Kotlin coroutine can do, which means it can be a generator, it can be an iterator, or more general purpose stuff like goal-oriented programming and cooperative multitasking. And another thing we saw is your asymmetric coroutines are sufficient. They can be, because they can be used to implement symmetric coroutines, which are much easier to implement and maintain. So this is an interesting example because we see why using coroutines everywhere may not be such a great idea, a small caveat. So in cooperative multitasking, like I mentioned, the interleaving of the concurrent tasks need to be deterministic. And with coroutines, which are inherently non-preemptive, there's this fairness problem that starts coming up, that are all my processes getting the right amount of time? And what if one is blocking the other? And in a kernel environment where you have the coroutines running in a kernel space, you have a bunch of different programs that are not part of the same program sort of cooperating to achieve certain goals, and having like a coroutine transfer mechanism over there may not be a great idea, because it gets very difficult to interpret where the bottlenecks are or what program is actually causing the coroutines to block, stuff like that. But at the user level, coroutines are generally part of the same program, and they're collaborating to achieve a common goal. So it gets much easier to debug and stuff. So even if you're having fairness problems, it's restricted, and it can be much easier. It's much easier to identify them and reproduce them, and it's not very difficult to implement. So yeah, why coroutines in Go? Coroutines aren't directly served by existing Go concurrency libraries, even though we show that we can use Go definitions to implement them. And a talk by Rob Pike, which was lexical scanning in Go. Another talk that I've linked, a really interesting talk. I won't go into too many details, but they were using Go routines connected by a channel, and full Go routines sort of started proving too much, and the parallelism that was provided by Go routines started causing races. But a full coroutine solution would have avoided these races because of concurrency, right? Only one coroutine can be running at a time, and that would have been a great idea over there, just to show some, So yeah, we talked about coroutines, we talked about threads and generators, and they all sort of start looking alike. And so let's try to differentiate them a little bit. So coroutines, like I've already mentioned, they provide concurrency without parallelism. So when one coroutine is running, the others aren't. Threads, on the other hand, they're much more powerful than a coroutine, but they come with more cost. And that's because it has parallelism built in. And the cost of the overhead of scheduling is also way more, because they have their own stacks, and they're much heavy, and it's much expensive in terms of context switches. And when you have something like this, you need to start adding logic for preemption, and there's the whole complexity that comes with that. Go routines, on the other hand, are just cheaper threads. So a Go routine switch will be closer to 100 nanoseconds. Generators, like in Python, like we've already talked about, provide less power than full coroutines because they're stackless. So it limits what you can do with a coroutine. Only your topmost stack is allowed to pass control between coroutines and or the subroutine and the coroutine pair. So yeah, let's start building an API for coroutines in Go using the definitions that are available today. And this, I mean, a lot of the talk is borrowed from Russ's proposal for implementing coroutines. So if you have questions, you can reach out to him. No. You can reach out to me as well. I'll just ask him. So yeah, it's very neat that you can do this using existing Go definitions. You have your Go routines and channels, and how channels work with blocking Go routines, and also Go support for function values. And that's all we see over here. So yeah, just to recap, your coroutine can do these things. You can suspend and run another subroutine. You can terminate and yield, or you can suspend control and yield. And we try to implement all of this. So we start implementing the package Coro over here. And so let's start with this. We want to be able to suspend our subroutine or the coroutine that's running, the caller in this case, and we want to resume. We want to pass control from caller, which means suspending control over there, and starting your coroutine. So how can we do this? Well, we can have them blocked on channels. You can have your coroutine blocked on, say, cin, which is waiting to receive from the caller. It can be an unbuffered channel. And your caller, all it needs to do is write into cin. And how will it block itself? Well, it can wait for something to read from another channel. It can, and let's call that cout. So after your coroutine has stopped functioning, it just has to write into cout, block itself on cin again, and wait to receive from and your caller receives this output in its cout where it was blocked, and starts functioning again. So this way you're sort of passing control back and forth. So yeah, just some the code over here. So you have this function new that instantiates a new coroutine, and you're instantiating these new channels, these unbuffered channels. And what we've already discussed, your coroutine is running like a Go function that's actually blocked on cin, while your resume is blocked on cout. So all your resume needs to do is unblock this Go routine by writing into cin, which starts your coroutine or your Go which is just a Go routine that's blocked on a channel, essentially. And once its function stopped running, it can write into cout and start running your resume function again, the caller again. So you have this sort of send-receive pair that's forming. Yeah, the coroutine is blocked on cin, so there's no parallelism, which is another important thing. Let's start adding the definition for yield to suspend the function, right? How would that look like? Well, all yield needs to do is block itself and unblock this caller that invoked it. So all you need to do is write into cout where the caller was blocked on, and it can start waiting on cin. And that's exactly what's happening over here. Your yield function is just it's writing into cout, and it's returning returning, which means that it's just blocked on cin. So yeah, we're just adding another send-receive pair here, and there's no parallelism that's happening. So let's pause for a little bit. Are these actually coroutines? Well, yes and no. They're full Go routines, and they can do everything an ordinary Go routine can. CoroNew, all it's doing is that it's creating Go routines with this resume and yield operation, which is just passing control back and forth between the coroutine and its caller. And unlike the Go statement, we are adding new concurrency to the program without the parallelism. So if you, like this is an example that he uses, that if you have a main Go routine running which starts 10 Go statements, now you have 11 Go routines running, and they can be running all at once. But with the CoroNew, even if you start 10 CoroNew calls, the parallelism of the program is still what it was before, just one. So your Go creates new concurrent parallel flows, while your CoroNew creates new concurrent non-parallel flows. So back to implementing a coroutine very quickly. Now, what happens if your caller, your coroutine stops functioning? It terminates, and then you try to resume it again. Your caller is now waiting on something to write into cout, but it deadlocks because there's nothing to write into cout. All you can, it's a simple solution with this would be have a global variable, say running. So as soon as your coroutine stopped running, just set it to false, and your caller, every time it tries to call a coroutine, can just be like, hey, is this coroutine running? And if it's set to false, no. You may think that having a global variable between, sort of like a shared variable between potentially multiple coroutines that are running, it can cause data races. But again, only one process can be running at a time. So that won't happen over here. Yeah, so very simply, we can extend our resume function to check if running is set to true. And and it's set to false in our coroutine that's running. As soon as the function stops executing, it's set to false. What happens if your coroutines panics? It's the same thing. We have nothing to write to cout, but we are waiting to hear from the coroutine. But now your resume function is sort of blocked, right? Yeah, your caller is blocked waiting for the news. Yeah, so all you need to do is you need to find some way of passing this panic to your caller, and you need to handle that panic. And that's what we can do here. So we can run a defer function over here. So say and check if running has been set to the correct value. So if your running is true and your defer runs, that means something went wrong in the middle. So your function ran, but the running was never set to false, right? So you know that something panicked. And all you can do is write a panic into cout, and your resume function can deal with it. And in this case, if it sees that a panic is coming into cout, it'll panic itself. Finally, the final thing is, if you want to signal to a coroutine that it's no longer required, which means your caller could be terminating, and your it might be panicking. So the coroutine associated with the caller need not be running anymore, and you need some way of passing this information. So what you can do is same thing. You implement another function, say called cancel, and all it does is that it tells your coroutine that, hey, I'm canceling myself, and you need not execute anymore. And you can pass this information via cin, which your coroutine is waiting on, right? So and the coroutine, all it needs to do is write back into cout, which the caller is waiting on, that, hey, I have success. I got your message, and you can cancel yourself. And that's what's happening over here. I've pointed to the code which I'm talking about, just so that you don't have to look at the entire thing. But your cancel func is just passing your error cancel sort of flag panic to your cin, which is read by your coroutine, and it handles it however it wants to handle it. And what happens if this coroutine tries to yield when there's nothing to yield to? Well, it can just check if you're in the yield function, right? It can just check what the value in cin is, and if it's panic, it can just panic out. Another interesting thing that happens over here is that remember we implemented a way of propagating panics up. So what happens if the panic that you transfer from cancel actually bubbles its way back up? You don't want you need a way to know that this panic came from myself, or it's an actual panic that happened in your coroutine. And all you need to do is check if it's my own panic, and you just check if it's equal to E or not equal to E. Yeah, so some runtime changes. I was talking to Russ about it yesterday. So it's pretty cool. So while we have a definition of coroutines that can be implemented in pure Go, he builds on an optimized sort of runtime for this implementation. And so some of the perf data that he collected, and I wanted to reproduce, but I got lazy. Passing values back and forth using the channel that we just implemented was approximately 190 nanoseconds per switch. And so what he did was he started marking these send and receive pairs for the compiler. So the compiler, instead of having to schedule these channel switches, it can do it more directly, by fusing them into a single operation. And so you bypass the scheduler entirely and jump between coroutines when you resume or yield. And this actually reduced the time taken by 38%, and was just 118 nanoseconds in this case. And another change he talks about is like a direct coroutine switch without the use of channels, because channels are pretty general purpose, and they can do a lot of things that you don't need for this sort of an implementation. And that actually just took 20 nanoseconds, which was 10 times faster than the original implementation. And that's super cool. So yeah, conclusions very quickly. We covered quite a bit. Thanks for making it here. We were able to show that having a full coroutine in Go makes it even more powerful for sort of generalized, robust concurrency patterns. We covered the basics of coroutines, the history, and why it's not as prolific as it should be. And we showed that what full coroutines are as different classifications for it. We showed the need to have coroutines in Go, how they differ from Go routines, and how they differ from existing implementations of coroutines in some other languages. And we also implemented an API using Go definitions purely and build on it to make it a little more robust. We showed what runtime changes can be made to make this implementation even more efficient. Yeah, I would want to go through the references, but I don't think I have the time. But yeah, if you want to take away one, the first one would be great. That's Russ's proposal for coroutines. There's a bunch that I have not covered from it. There's also a bunch of videos by Gornishanov. That's where the negative cost abstraction came from in CPPCon, Adi Shavit, and yeah, lexical scanning by Go. I've also attached the papers that I've read. And yeah, if you want to look at these slides, they're on my speaker deck, Roy RA. Yeah, thanks a lot.